There I am. All of this made my computer crash just so I could be on the screen. So thanks for the introduction. I'm really sorry for the delay. This is the setup I use for teaching. I've been teaching since like January 6th, and this is the first time my computer's crashed. So that's awesome. Okay, jumping right into things. I'm going to talk about couple cluster theory for light matter interactions. Most of the time I talk about RDM methods, so this is a very different talk for me. So hold on to your hats. It's going to be fun. I'll start off with my acknowledgements because I don't know how much people will be paying attention to this in the end. So the students that were involved mostly in this work today are Brandon Cooper, Daniel Nascimento, who's now faculty at University of Memphis, Lauren Coulias, who was an undergraduate with me and is now a graduate student at University of Washington with Xiaosong Li, and which way do I move? Xiaosong Li. It's NSF supported work. And the code, a lot of the code I'm going to be talking about is available in GitHub in this package I call Hilbert, which is a plugin to Sci4. And then the next thing I'll point out is I have a new outreach activity I'm trying to do on Twitch. That's my username. If you want to follow me, this is the point of it. I call it Supercoding Fun Time with me, Eugene. And we'll do things like random projects that are just kind of fun and don't have much to do with science. So here you see I have trained a bunch of squares to flock like birds, that kind of thing. I'll also do some chemistry related programming projects. So you should, yes, all right, I got a follow. I'm so excited that actually worked. So if you follow me, that happens. That's awesome. There's also a chat. You could use the chat, but that would probably be really annoying. So don't do that. Okay, anyway, moving on to the talk. I'm talking about couple cluster theory, and specifically I'm going to be talking about mostly time-dependent couple cluster theory, or time-dependent methods for electronic structure. And there's basically two reasons why you would ever want to do time-dependent electronic structure. That might be, one might be you're interested in situations where you have strong fields or multiple laser pulses, basically anytime you're beyond the linear response regime. And so you need to use real-time approaches to watch how a wave function or density evolves in time to capture the physics of the problem in its entirety. So two examples I have here are plasma and molecule interactions. So I have a driven resonant energy transfer between some molecule and a silver nanoparticle in this case. Or what I'm more interested in recently is cavity mediated chemistry, where you have a molecule inside some sandwiched between two mirrors. And then you can create interesting hybrid light matter states inside this cavity. You can think of the plasmonic molecule, the plasma molecule situation as a cavity type problem too. The second case where I might be interested in time-dependent electronic structure is a more practical case where, say I'm dealing with a system that's very large and has a large density of states. If I do an iterative diagonalization to get out excitation energies, depending on how big the system is and how dense the excitation manifold is, I might only get out a handful of the states I'm interested in. Whereas if you do a time domain simulation, that's this RTTD-DFT, you can get out broadband signals from a single calculation. So I'm going to start by talking about the second category, practical benefits of working in the time domain. This isn't my work. It's Ken Labata's work. I just like the figure. So the point here is diagonalizing a Hamiltonian in a large system with a high density of states is not trivial. So the basic idea in a time domain calculation is to tickle the system with light and then record some observable like dipole moment in time. And then the Fourier transform of that dipole moment can be interpreted as an absorption or an emission spectrum. The benefits you get here are you have spectral information over an arbitrarily wide energy window in a single time domain signal. And second, there are reduced storage requirements compared to diagonalizing the Hamiltonian, the full Hamiltonian. And this is especially true when you're thinking about many body methods. And you might want, say you want 200 roots, that means you need 200 copies of your wave function plus 200 copies of sigma vectors times 8 or whatever is required by a Davidson algorithm. So you need many, many copies of the wave function. But in these time domain methods, you only need a handful. So that's great. Okay, so these explicit time domain ideas are pretty popular in the DFT community. And I don't know, when I first got to FSU, I started thinking about how to do this in a many body framework. And so I was thinking about couple cluster in particular and how to extend this to a time domain situation. So starting with the ground state couple cluster theory, I have this should be familiar on SOTS to a lot of us, where we have our couple cluster wave function is given by this exponential operator acting on a Hartree-Fock reference determinant. And this cluster operator contains single excitations, double excitations, however many excitations you want to include. If you wanted to extend this to a time domain theory, you could build time dependence directly into the T amplitudes and the orbitals. But there's a couple of problems here. One, the equations that you end up with are nonlinear and very complicated. And the nonlinearity makes it difficult to integrate because of numerical problems. And the second problem with couple cluster theory is you need to propagate both left and right hand couple cluster wave functions because it's not a Hermitian theory. And so that just basically means you have to do twice as much work as you might think, as you have to do in DFT, for example, in addition to the increased cost of couple cluster. So thinking about how to get around this, you could work within an equation of motion couple cluster framework, which in its usual form, we have excited states that are determined as eigenfunctions of this similarity transformed, normal ordered similarity transformed Hamiltonian. And then these excited states are eigenfunctions of this operator, and all the information about the configurations involved in the excited state are contained in this R operator. Okay, so the nice thing here is my equations are no longer nonlinear because R is a linear excitation operator. However, the normal ordered similarity transformed Hamiltonian is still non-Hermitian, so I still have to propagate both left and right eigenfunctions if I want to get something like a time-dependent dipole moment out of the calculation. So it's still twice as expensive as it should be, really. Okay, thinking about how to get beyond that second limitation, we can think back to Fermi's golden rule type picture of what the line shape function should be. So I start with this expression that should be familiar. It involves a transition dipole moment between initial and final states, an energy matching criterion, and a sum over initial densities of states. And then I have this line shape in the Kessieth direction, so XYZ. If I put on my graduate quantum mechanics 1 hat, I can do a few manipulations to simplify this. 0 Kelvin, I only have my ground state populated. I can replace the delta function with a Fourier integral, and then I can represent the final states in the framework of EOM couple cluster theory. And you end up with this result. There's a bunch of things here, but nothing's more complicated than what shows up in standard ground state couple cluster theory. You have a reference determinant, you have a CC de-excitation operator, you have the complex conjugate of the time evolution operator, and you have a similarity transform dipole operator. And we should just take a moment to marvel at this gorgeous result, because this is beautiful to me. This is exactly the same thing as a normal Fermi's golden rule line shape function, but at the time-dependent couple cluster level of theory. We take that beautiful result, and then we can define left and right dipole functions. So here's a left-hand dipole function, a left-hand dipole function and a right-hand dipole function. And now I have this expression instead for this expectation value. And now I can choose to act either to the left or to the right with my time evolution operator, and I get two equivalent expressions that look like autocorrelation functions. So these are dipole moment autocorrelation functions, and the Fourier transform of them, which is all this is, gives me an oscillator strength. It's actually the real part of the Fourier transform of that dipole autocorrelation function. And both of these give me equivalent results. So I could choose to propagate in either direction. Okay, that's great. What a fun result. To validate this, we used low order couple cluster methods, so just CC2. And in this figure, I have spectra for a few small molecules. The black sticks are from standard EOM CC theory, where the blue dashed line is artificially broadening that by 0.2 and change EV. And then the red lines correspond to time-dependent EOM CC calculations broadened by a consistent damping constant to give me the same full width at half max. And then we see for the smallest molecules, these spectra are essentially identical. I can't really tell the difference between them. But then small differences start to emerge in butane. It's a tiny difference. I wouldn't worry too much about it. But these larger differences might seem problematic at first in malonaldehyde, for example. And the reason that we see these large differences, despite the fact that the spectra are very similar at low energies, is because when I ran my EOM CC2 calculation, I asked only for 100 total excited states. So the blue curve is wrong at this point. There's spectral information missing. So this is the entire point of wanting to do a time domain calculation, because I get all this information without having to worry about how many states I need to ask for. And that problem becomes exaggerated as you go to larger and larger systems. So obviously, none of the information, say we wanted in this region from the time independent calculation, we didn't obtain any of that. Cool. I mentioned that propagating to the left or to the right gives you completely equivalent line shapes, and this is numerical evidence of that. These are indistinguishable on this on the scale of this figure. I have propagating to the left and with the blue dashed line, and propagating to the right. I'm sorry, acting to the right with the time evolution operator in red, and these are indistinguishable. Okay, so this seems great, but there are a lot of challenges associated with this strategy for getting excited state information. Real-time methods generally require a long simulation time to fully resolve spectra, and a discrete Fourier transform has very poor convergence properties. So here I'm illustrating that for carbon monoxide in a double zeta basis set with increasing simulation times. You can start to see this peak in particular at about 14 eV. We can't resolve it at all until maybe 100 femtoseconds. I'm confident that it's 2 peaks, and then it's fully resolved way out here at 800 femtoseconds. Here, this calculation takes about 80,000 total time steps. And if I'm doing something like RK4 to do my integration, that means I'm going to have 4 sigma vector builds for every single time step. Sigma vector is just h times the wave function. So I'm going to have more than 300,000 sigma vector builds for this calculation. That is an absurd number of sigma vector builds. So this is basically an unusable theory at this point. Modeling high energy features is going to make things even worse, because I'm going to need tiny time steps to be able to capture all of the high energy features in K-edge spectrum, for example. So what can we do? Well, we can introduce approximations to the Fourier transform. We could use Pade approximants for this purpose. I think this is a pretty common idea in signal processing people, but as far as I know, Ken Lapata is the first one to bring this to the quantum chemistry community. He can correct me, or he can just let stay quiet and take credit for it.
I'll correct after.
Okay, cool. Well, for the next 30 minutes, you can have full credit. Anyway, this is how I learned about it, at least from Ken's paper. So you take your original dipole autocorrelation function and evaluate the discrete Fourier transform in this way, where I have a coefficient C is equal to the dipole autocorrelation function at a given time, and Z is equal to this exponential involving my frequency and the time step. And then I can take the diagonal Pade approximant to this term, where I have this ratio with different coefficients A and B that are just determined from some set of linear equations. And by some mathematical magic that I don't fully understand, this process converges much more quickly than the discrete Fourier transform. So for example, if I do a calculation at a more sophisticated level of theory, because I have a better method that I can do larger calculations on, at the CCSD level of theory in a pretty big basis set at the K-edge and carbon monoxide, if I propagate for 2,000 time steps, I'm pretty confident that I have my principal K-edge feature at about 289 eV in carbon from the Pade signal processing. But with a Fourier transform, I have no idea what spectral information is here. I can go out to 5,000 time steps, and now I know from Pade that there are some Rydberg peaks at higher energies, but I still know nothing from the Fourier transform. I can go all the way out to 20,000 time steps, and now I can start to be pretty confident about the spectra from the Fourier transform. The Pade is definitely fully resolved at this point, but it really takes about 100,000 time steps to fully converge the discrete Fourier transform in this case. So here, Pade representation of the Fourier transform can reduce the cost of your calculation by a factor of 10, because you really need only about 10,000 time steps to get all the peaks, which is amazing. Factor of 10 speed up. So that's great. That allows us to get broadband spectrum from a single simulation on reasonable systems, carbon monoxide, at a reasonable level of theory, CCSD, in a pretty large basis set. So you can see from one calculation, you get UV vis data, you get carbon K-edge data, and you get oxygen K-edge data. And then you get a bunch of other nonsense peaks as well. that are above the ionization threshold. Doesn't matter. We will ignore those. Just pay attention to the colored ones for now. Okay, armed with these tools, we can do evaluate high accuracy X-ray absorption spectra. So for example, to give you an idea of couple cluster accuracy for the carbon and oxygen K edges, I have experimental peak positions in gray, and then my computed peak positions in either red or blue. The total spectrum is in black. In time domain calculations, it's very difficult to tell exactly what excitation you're looking at because you don't have the wave function for that state. But you can at least tell the difference between different features based on their symmetry. So I can tell the difference here between pi states and sigma states based on whether or not I'm looking at the z component of my moment correlation function or the x or y components. Okay, that's fun. In terms of mean errors, you get an error of something like 1.25 EV from an EOM couple cluster calculation, and that compares with on the order of tens of EV, on the order of 10 EV from something like B3Lib. So that's nice. Okay, there are still additional challenges to overcome in this framework. As I already said, this is a very expensive calculation to do. However, I can do PAD-A and I can get this down to maybe 10,000 time steps, but that still means I'm doing 40,000 sigma vector evaluations, which is still a large amount of work. So can we at least reduce the cost of the time integration? Meaning I may have to take 10,000 time steps, but can I find some kind of integrator that lets me get to that number of time steps with less work? And the answer is yes, with a better integrator than RK4. Some of you might be thinking RK4 is a terrible integrator and no one should ever be using it, but it's actually pretty common to use with many body methods. I'm not 100% sure the reason of that. One reason could be people in DFT community use Magnus propagators that depend on commutators of the Hamiltonian. But in many body theories, once I turn my laser off, the Hamiltonian's time independent. So then all of those commutators are zero. So I'm not sure that you can apply Magnus propagators to many body methods. Someone can correct me if that's wrong, but that's my understanding. Anyway, you can go beyond RK4. You could use develop either implicit or explicit symplectic integrators that obey some energy conservation laws, things like that. You could develop Chebyshev integrators. There are cases where you could get away with propagating only the real component of the wave function, so that would speed you up by a factor of 2. Or what I am interested in is something called a short iterative Lanczos propagator. And this thing significantly reduces the number of sigma vector evaluations that are required for a calculation. So I'll quickly explain to you how that scheme works and show proof. Proof is hard. I will demonstrate to you that it can greatly speed up calculations. So our goal here is to propagate some wave function, some function in time according to the time-dependent Schrodinger equation. And these sigma vector evaluations are what are the expensive thing in the calculation. So the solution from the short iterative Lanczos point of view, which is a very old idea, is to approximate Hn with some representation in a reduced subspace. I'll call that Hp. And then I'm going to propagate a reduced representation of our wave function for some short amount of time using Hp, the approximate Hamiltonian. At some point, that Hamiltonian is not going to be good enough to do dynamics anymore. So I need to transform back to my original representation and build a new approximation to Hp. Every time I build a new Hp, which is an approximation to Hn. Every time I build a new approximation to Hn, I have to do a bunch of sigma vector evaluations. But the point is, in this procedure, the total number of sigma vector evaluations I'll do is way less than I would have done if I just did an RK4 propagation with the original Hamiltonian. And you can get away with pretty small Lanczos dimensions in this case, 20 or 30, gives you a reasonable speed up in accuracy. A note here, CC is a non-Hermitian theory, and yet we apparently don't need to modify standard Lanczos procedures for Hermitian matrices. We can just apply a normal Hermitian Lanczos procedure. Okay, as just a brief demonstration of how this works, I can show you the average number of sigma vector evaluations required for a UV vis calculation on a bunch of small small open and closed shell molecules. So in red, I have the number required by RK4, which is just determined by the number of time steps I have to use in this simulation. And then in the blue, I have the number of time steps required by SIL for various subspace dimensions. And you can see they drop off pretty quickly even at a dimension of only 5, you get some improvement over RK4. And then past a dimension of 20, you really don't get that much improvement over RK4. I can think about how much error is incurred in my calculation by propagating in this reduced subspace by defining some kind of error metric. Here I'm going to use something we call a normalized integrated error, which is just defined as the difference between my oscillator strengths from SIL and my oscillator strengths from RK4, which I'm going to say are the exact ones, normalized by the oscillator strengths from RK4. This prime in the integral means I'm only integrating over a region that I'm interested in. So in this case, for UV vis, I should call it low energy, not UV vis. I'm going from 0 to 25 EV in this case. Okay, and you can see that the NIE drops off extremely rapidly. And again, at a dimension of about 20, you stop to see much improvement in the error. So based on this, we sort of conclude that a subspace size of 20 is a reasonable one to use. We could go larger and go out to 50, but the problem is, as you make the subspace size bigger, you have to store more and more copies of the wave function. So in this case, I have to store 20 copies of the wave function, basically. Out here, I would have to store 50. So it's just balancing that extra cost with the speed up, speed get. So these are average errors to show you visually that the spectra obtained from SIL and RK4 are very similar. Ignore the green line. The red and blue lines here are spectra from an RK4-based calculation and an SIL-based calculation, and they're indistinguishable on this scale. So this is with a dimension of 20. So it's pretty accurate. Okay, this is the same figure, except now I'm talking about K-edge features of the same molecules. And you can see with the normalized integrated error again. And you can see basically the same story. The number of sigma vector evaluations required drops off very rapidly, much more rapidly in this case than in the case of UV vis spectra. And the normed integrated error again drops off. And after about 20, there's no reason to move past this because I'm not improving my error very much. I should note that the benefits of SIL over RK4 are obvious in this case, but these results are skewed by lithium that's in this set. Lithium is 64 times more efficient in the SIL framework than using RK4. In general, the other cases, we see about a factor of 4 to 9 improvement over RK4. So you take our original calculations, and then you add PAD-A approximants, and you add a better integrator, and we can do calculations about 50 times more efficiently than we used to be able to, which is nice. Okay? And hopefully we'll be submitting this paper tomorrow if Brandon, who may or may not be here, has finished making the final changes. I don't know what that slide's supposed to be. Oh, okay. Again, Elancho's dimension of about 20 is what we determined to be optimal. This framework is fun because you can do, this time domain framework, this moment-based time domain framework is fun because you can do different types of spectroscopy just based on the operators you include in your line shape functions. So here, oscillator strengths come from electric dipole. If I replace one of my electric dipoles with a magnetic dipole, then I can calculate rotatory strengths, which is fun. And then we can simulate electronic circular dichroism. So this is work with that student Daniel, who's now faculty at University of Memphis that came out a couple of years ago. And it's the same story. We reproduce frequency domain couple cluster results with these time domain calculations, and then we get information over a much broader range of energies than the time domain calculation gave us, simply because we didn't ask for enough roots in the time independent calculation. We've also extended this framework to relativistic couple cluster inside the exact 2-component framework. I don't need to go into these details, but basically I don't need to go into these details. We can do relativistic calculations. From my point of view, once the X2C procedure is done, I just need to generalize my code to be complex and spin broken. Since it's a time domain calculation, it's already complex. So we just need a spin broken formalism to do X2C. And we do that, and we can now calculate things like zero field splittings, where for the sodium D line, we basically nail experiment even in a tiny basis set. We're within 0.2 milli EV of experiment. And then similarly good results for other systems. Okay. And then now in the spin broken framework, we can look at spin forbidden processes. And so we can yeah, we can look at spin forbidden processes. And the errors from couple cluster are much smaller than the errors from DFT. Great, it's very accurate. Okay, to summarize this part of the talk, I hope I have time to keep talking. We have a time-dependent EUMCC formalism that's formally equivalent to EUMCC, and we validated it at a couple of levels of theory. I think the most useful scenario is probably for X-ray spectroscopy, if I want to look at K or L edge features in large molecules. The only problem with this approach is time stepping is extremely expensive, but you can mitigate that with either good signal processing using the Padet representation of the Fourier transform, or fancy integrators like short iterative Flanschos. It's still very expensive, but it's much less expensive than it was 3 years ago. And in terms of current directions, everything we've done in this framework is basically good and usable for laser-driven simulations that are like the conventional way that people do time domain calculations. So we can use this machinery to study actual electron dynamics or linear spectroscopies. And this collaboration with Jiasong Li and Cronus Quantum, we're also developing standard frequency domain relativistic couple cluster methods. Anybody? I don't know, do you guys do questions in the middle or at the end? We'll just do them at the end unless someone has a burning question, because I'm going to switch gears a little bit. Okay, back to this motivation slide. Why do we do time-dependent electronic structure theory? Well, I covered this class where I'm just interested in the practical thing. I want to do a broad window, energy window, in one shot. I don't want to have to worry about iteratively diagonalizing some giant matrix. The other reason I would want to do time-dependent electronic structure theory is because I have to. The physics of my problem demand it. So strong fields, multiple laser pulses, that kind of thing. Okay. So specifically, I'm going to spend the rest of the talk talking about strong light matter interactions. Interactions between nanoconfined photons and molecular degrees of freedom can lead to the creation of interesting states called polariton states, which have all sorts of interesting and surprising phenomena associated with them. Here, I'm stealing a figure from Jay Foley, who was studying a diazobenzene molecule strongly coupled to a nearby nanoparticle, and looking at the sister-trans isomerization reaction here. And the idea is you can, which occurs in the excited state. So normally you would excite and you'd come down here and you'd have a 50-50 probability of falling into the cis-trans bin. But if you can strongly couple this system to light, then you can have a photon state that looks like the ground state of the molecule plus whatever the photon energy is. And if the coupling between the photon and the molecule are strong enough, you can create hybrid states here where the wave packet can hop from one surface to the other. So in this case, it has a possibility to hop from this upper polariton to the lower polariton, and then you have an increased probability of falling into the trans basin. So this is a way to, by strongly coupling the system to light in a cavity or with a plasmonic particle, you can increase the rate of isomerization here. There's a gazillion examples of people looking at similar types of cavity-mediated chemistry, from catalysis, changing singlet fission rates, mediating electron transfer, lasers, long-range energy propagation, you name it. It's relevant in quantum information science, relevant to spin crossover complexes, changing transition temperatures there. There's a lot of really interesting chemistry here. So that's what I've become very interested in, and it's about what half of our group is working on now. I have some toy codes that model this sort of thing. So here's one other example that I can show you where strongly coupling a molecule to a cavity can give you some interesting results. So here's a formaldehyde molecule treated at the CIS level of theory, configuration interaction with singles, in a pretty big basis set. And you can see here, there's an avoided crossing between these two states. It occurs at about 11 eV. So if I could design a cavity that had a resonant frequency at 11 eV, then I could modulate the topology of this conical intersection, this avoided crossing, and maybe change the excited state dynamics of this molecule. So if I put this thing in a cavity of frequency 11 eV, then I can have photon states in that cavity, which will just basically add, if I add photon plus molecule, I get the energy of the ground state plus the energy of the photon. So that state would look something like this. And then if that's electron and photon couple strongly to each other, then all of these states can mix together. And you get something that looks like this, where Orange represents photon character, blue represents electron character. So you get this photon state that's orange. When I come close to electron states, I get hybrid state that's a mix of purple and orange. And then I come out of this region and I get all photon character again. And you can see here where there used to be only one bound state. Now I've created two bound states that have significant electronic character. So this will definitely change, I think. It would definitely change the the excited state dynamics of this molecule if you placed it in a molecular cavity, a high quality cavity with an appropriate frequency. Okay, this is why this is interesting, because you can do neat stuff like change your excited state surfaces. Okay, I'm going to talk about mean field cavity quantum electrodynamics, which is how you model this type of phenomena, and I'm going to talk about couple cluster based cavity quantum electrodynamics. In both cases, I start with the Polyfier's Hamiltonian for one cavity mode within what's called the cavity-Born-Oppenheimer approximation. It just means my nuclei are fixed. And in something called a coherent state basis. That detail doesn't really matter, but that's what this is. The Hamiltonian has normal electronic terms. It has a term for the cavity mode with photon operators, bosonic operators for creating and destroying photon states. There's an electron-photon coupling term. This is what the photon dipole operator looks like. And this is what the dipole operator looks like in the coherent state basis. So basically, this is dipole interactions. And then there's another term called the dipole self-energy that looks like this. It's very strange looking. It looks like the variance in the dipole moment. Okay, my wave function for the system in a mean field framework is just a direct product of a Slater determinant and a zero photon number state. That means it's a state with zero photons in it. Zero photon number state. And then I can determine this Slater determinant just by doing some kind of modified Hartree-Fock procedure. In the coherent state basis, this is the only term that will enter in Hartree-Fock theory. And all of the integrals you have the same structure as the two electron integrals that are in the normal Hamiltonian. So you can just add these terms to your normal your J and K builds if you're familiar with how Hartree-Fock works. Okay, now I'm specifically going to talk about mean field CQED in the time domain. And so you can do time evaluation in the same way that you could do time-dependent Hartree-Fock theory, which is where basically you can derive equations of motion by looking at this commutator of the dipole operator in the Hamiltonian. And if you throw out all of the connected two electron pieces, then you end up with time-dependent Hartree-Fock theory. And you can also define equations of motion for how the cavity mode, the photons in the cavity mode evolve. And in this case, I have mistakenly generalized this to 3 cavity modes. So there's three coordinates, but up here I was only talking about 1. And then you can build in dissipation as well. Here I'm doing it with a Lindblad superoperator to account for the decay of my plasmon mode. This is kind of old work, and it's just a proof of concept. I actually am using a slightly different Hamiltonian than here, but it's the same idea. So this is mean field CQED in the time domain. As a proof of principle, I can have a sodium dimer interacting with a plasmonic nanoparticle. Now, there isn't actually a nanoparticle here. It's basically a 3D quantum harmonic oscillator, or polarizable dipole. And it's parametrized using Mie theory. So the frequency, dipole strength, and the lifetime that go into that model Hamiltonian on the previous slide all come from fitting to Mie theory. And then I can describe this, I said it was sodium, it's lithium. I can describe that in a normal ab initio way. Okay, so the fun thing here is I can place this molecule near this cavity and calculate something like, I believe this is a scattering absorption cross-section. And I can see that at infinite separation, I can look at the scattering cross-section from the nanoparticle or from the molecule, and clearly this is dominated by the nanoparticle. And there is a sigma G to sigma U plus transition from my atom. As I bring these guys close together, even though this feature is super tiny, it can interact in a very complex way with the oscillating dipole moment on the plasmonic nanoparticle, and you can get this kind of transmission dip that is looks like a Rabi splitting for this system. And it's kind of neat that such a small molecule, a tiny feature at infinite separation, can lead to such a large pronounced change in the scattering cross-section for this giant nanoparticle. Nice thing about using an ab initio framework for these atoms, I didn't go into details most of the time. Oftentimes people use simple model systems for CQED, like Jaynes-Cummings model. You just have a 2-level quantum emitter interacting with a cavity mode. in this case, because I'm treating this molecule in an ab initio way, I can see that as I rotate the molecule, so its axis is not aligned with the external field I've applied, then I don't see the transverse excitation in the sodium dimer anymore. And I start to see, I'm sorry, I don't see the longitudinal excitation anymore. I start to see this transverse one that shows up. This tiny blip looks pointless, but I think it's kind of neat that it shows up, because you wouldn't know that this peak is here if you had done this in a Jaynes-Cumming type framework where you only have a two-level quantum emitter. So benefits of using an ab initio framework. Slightly more realistic looking system, I can see the same thing for, say, a Bo-Dippy molecule interacting with a silver nanoparticle. It's the same idea. As I bring the two systems close to each other, the presence of the Bo-Dippy molecule, which on this scale, I can't even see its scattering cross-section, it can lead to non-negligible changes in the scattering cross-section for my nanoparticle. With this Rabi splitting, anytime you see a feature like that, there's going to be some kind of phase shift in your dipole, relative dipole moments. So if we can see that in our calculations, which is kind of neat. So if I look at how the dipole moments for the molecule and the plasmon decay in time, at infinite separation, I can see that the plasmon dipole moment is much bigger than the molecular one in blue, and they're oscillating in phase with each other. If I bring them close together where they start to strongly couple with each other, I'll see a dipole phase reversal. So at early times, the dipole moment for the plasmon is 90 degrees ahead of the dipole moment for the molecule. So you can think of that as the plasmon dipole is driving the oscillations of the molecular dipole. At some point, the plasmon decays, there's a phase reversal, and then the molecule can start to dump energy back into the plasmonic mode. So now the molecular dipole moment is 90 degrees advanced compared to the plasmon dipole moment. And you can see this beautiful phase shift at 92 femtoseconds, and that phase shift is sensitive to the distance between the two systems. Neat. It doesn't matter. This is just how that phase shift changes in time. Okay. How long am I allowed to talk? 10 more minutes?
Sure, that works.
Okay. I'll wrap up with cavity quantum electrodynamics couple cluster theory. That was old work. I'm no longer interested in the mean field framework. I'm interested in couple cluster framework. And I'm not doing anything in the time domain anymore. So this is all time independent. So in the couple cluster framework, you use the same model Hamiltonian that has the electronic Hamiltonian and then these cavity interactions and the cavity mode. I still start with a direct product of a Slater determinant and a zero photon number state. And then my CC wave function is given by the exponential operator acting on this reference wave function. The difference here is now my CC wave function can have electronic pieces, it can have photon excitations, and it can have coupled electron and photon excitations. Those, I already showed you this electronic piece here. I'm just talking about CCSD, so I have single and double excitations. My photon operator, if I allow one photon excitation, this is my photon excitation operator. U is an amplitude. And then my coupled terms look like the T amplitudes from standard coupled cluster theory, except they're augmented by this bosonic creation operator. This is known as the QED CCSD1 model. This is a kind of a misnomer. It's not real QED, it's cavity QED. So it's unfortunate that that's what the name is in the literature, but that's what it is. I should have updated this reference. This is from the archive, but this paper is now published in PRX. Anyway, this is their model, so I'm just following that model. And you solve for amplitudes in the usual way, doing projective solution to the Schrodinger equation. I don't really, this doesn't matter. Here are some tools you can use to generate such equations, and I've implemented this code in this package called Hilbert. I've written up a paper on it. You can read that if you want. Hilbert's a giant plugin to Sci4, so there's a bunch of other methods in there if you want to play around with those. And I have several QED coupled cluster methods. One of them's broken. Whoops. Okay. So the question I wanted to ask first, I haven't done any EOM, I haven't done any excited state calculations with this framework yet. So the question I wanted to ask was, could cavity modulate the ground state properties of a molecule if the molecule is strongly coupled to it? And the answer is yes, but let's explore that first. So I wanted to look specifically at ionization potentials and electron affinities for a silly series of molecules, the sodium halide series. I chose these originally because they have giant dipole moments, and naively I thought, big dipole moment, they should interact strongly with the cavity. But we'll see in a second that that thinking is not completely correct. I'm exploring a range of cavity coupling strengths from 0, which means no cavity, up to 0.05, which is the strong coupling nearing the ultra strong coupling regime. And my cavity is oriented such that the polarization of the cavity mode is along the molecular axis. I'll just tell you, IPs aren't particularly sensitive in these molecules to the presence of the cavity. The largest change I can achieve at the QED-CC level of theory is 0.08 EV, which is not 0, but it's not terribly crazy. EAs, on the other hand, can be altered quite a bit. This table is kind of a nightmare. Sorry. On this line, I have my cavity-free EAs for these molecules. I'm just going to highlight sodium fluoride because that's where I see the largest changes. Going from a cavity-free case to a coupling of 0.05, my QED EAs can change as much as almost 0.2 EVs, which is quite large. And my QED Hartree-Fock EAs can change by 1/4 of an EV, which is also quite large. It's interesting. Okay, so the presence of the cavity clearly does something that changes this ground state property. I mentioned that I chose these molecules because I wanted to couple strongly to the cavity, and naively I thought a strong dipole moment would help me achieve that. That's not quite the whole story here, and I can see that if I explore how the EAs change when I change the relative orientation of the molecule and the cavity mode. So here I'm going from an orientation where they're aligned, I'll call that 0 degrees, to an orientation where they're perpendicular, I'll call that 90 degrees, and I'm going to look at the EAs along that as I modify that angle. The dashed lines here represent the cavity-free values. So I can see, I'll focus on sodium fluoride. I can see my EAs drop quite a bit. That's that 0.18 EV just by placing the molecule in the cavity. And then the surprising thing is, when I bring the molecule out of alignment with the cavity mode, I get an even larger change in the electron affinity. This is the exact opposite behavior than I was expecting because the dipole is not aligned with the cavity mode anymore. So that's clearly not what's important. What's even more interesting is at the Hartree-Fock level of theory, you see really large changes. You can see this is clearly, the molecule is very sensitive to the alignment with the cavity, and the ionization potential is the most modulated relative to the field-free dashed lines, sorry, cavity-free dashed lines at the perpendicular arrangement. And in this case, the sign for the QED-HF electron affinities actually changed. So we have qualitative change in the ground state properties of the system just by placing the thing in a cavity. It's amazing. Can the density displacement tell us anything about this phenomenon? So I'm going to look at the difference in the density of the molecule inside the cavity and outside the cavity. Red's going to be an electron-rich region compared to outside the cavity. Blue's going to be an electron-deficient region compared to outside the cavity. So for my neutral molecule, I get this neat lobe structure where along the cavity mode, I get an increase in electron density when I put the molecule in the cavity. And perpendicular to the cavity mode, I get a decrease in electron density. And that's the same at both of these centers. You can't really see it here, but it's the same at both these centers. If I put the anion, which is the other species I care about for my EA, inside the cavity, then I see something completely different. I still see this nice lobe structure at the fluorine center, but sodium looks completely crazy. There's a huge increase in electron density on the exterior of the molecule. And also this lobe structure has given way to a more complicated lobe structure that has some oscillations to it, okay? Neat. So the anion, from this, I can see that the anion is much more sensitive to the presence of the cavity. And that makes sense because if they were both equally sensitive to the presence of the cavity, my EAs wouldn't change. So this is why my electron affinity changes, because my anion doesn't like being in the cavity. If I change the polarization of the molecule, of the cavity relative to the molecule, I see, I mean, this looks different from in this case, but it's actually quite similar. I have an increase in electron density along the cavity mode, parallel to the cavity mode, and a decrease perpendicular to it. That's the same as in this situation. So the cavity deforms the electron density in a very similar way, and that's reflected in the energy for the molecule. This is the energy of the neutral molecule as I rotate it from 0 degrees to 90 degrees, aligned with the cavity mode to perpendicular to it. The energy doesn't really change, okay? So the molecule doesn't like being in the cavity, but it doesn't really care how it's oriented. Contrast that with the anion, the density deformations are very different in this case. I've lost that lobe structure at the fluorine center, and I have much more electron density at the exterior of the molecule at the sodium center when I have my polarization in this way. And also, you'll notice I don't have this lobe that's parallel to the cavity mode in this case. Everything's still kind of polarized in this direction. So this is consistent with the energy change I observed for the anion inside the cavity as I change the orientation. The anion is very sensitive to that orientation. How fun. Okay, lastly, I can ask, because the reviewers asked me when I got my reviews back after 7 weeks, how general is this phenomenon? Well, I can see it in other sodium compounds where I see large changes in the EAs at the couple cluster level of theory on the order of 0.2 EV. If I look at other molecules, I can realize pretty large changes, 1/10 of an EV, in both IPs and EAs, but I really don't trust any of the results. So I would rather not discuss them because I'm using an unrestricted CC formalism, so everything's spin contaminated, and it can be huge for some other molecules. I should say, though, with respect to the molecules I looked at, the halide series and also these other sodium compounds, they're really not spin contaminated. So S squared is 0.76 for doublets, and then I can't find any spin broken singlet states. So I'm pretty confident in the quality of the results for those sodium halides. Okay, to summarize this part, the big point is I have developed this code, huzzah. It's available in Hilbert if you want to play with it. Cavity interactions can change your ground state properties, sometimes qualitatively, at the Hartree-Fock level of theory. So that's an important point to note, that the difference between the Hartree-Fock and couple cluster results show just how important correlated electron-photon interactions are in this framework, because you get qualitatively different results at the Hartree-Fock and couple cluster level of theory. And the other surprising thing is a permanent dipole moment is not needed to modulate the properties of a ground state properties via strong coupling to the cavity. Maybe the electrons need to be polarizable. I'm not really sure. The relevant term in the Hamiltonian is this dipole self-energy. So if you have a molecule that has a large variance in its dipole moment, then it will interact strongly with a cavity. So it's possible to take, say you had a molecule who wanted to know if its IP and EA changed, you just do a Hartree-Fock calculation and calculate this dipole self-energy, which is pretty easy to do at the Hartree-Fock level. And if it changes a lot, if it's large for the cation and small for the other neutral and anion, that would suggest that the IP is going to change a lot. Cool. Okay, that's all I have. Same acknowledgement slide. You guys should all follow me on Twitch so you see the follow thing pop up again. And with that, if there's any questions, I will take them.